some values for my induced velocity at point A. Okay, but point A is just an arbitrary point. It can be any point. It can be at this point. It can be at this point, wherever my pointer is. Okay, doesn't matter at all. Okay, so this is just for simplicity's sake, right? Where you do some simple math, trigonometry functions, right? For us to get the induced velocity at this point. Okay, so you can see right from here, your B and C, there are actually two sides of filament here. Okay, so in essence, right, you can see this as B to C is the span of the wing. Yeah, and the filament really is just like a winglet there. Okay, because where there's a winglet, you can actually change the circulation and reduce velocity. Alright, so how do we start this question? Alright, so the first thing that you must have actually is this equation here. Okay, can you all write this equation down, please? For those who just came in, this is for last week's lecture, the last example. So you notice the filament length is the whole thing here, okay, that's what the distance S here. So I'm looking at one point of interest, okay, that means where my circulation is to the point of induced velocity. That's why the distance between this point and this point is your R. Okay, that's your distance here. Okay, so a beta right here is the arbitrary angle, okay, because from B to point A, okay, you can actually define within B to A, right, by your R distance or S distance, and also a certain angle here. Okay, so this is the arbitrary angle that we will have to introduce, but later on we have to eliminate as well. Okay, so we must know what is this angle equals to. So if you look on this trigonometry diagram, if I have a beta here, okay, I have got my S and I got my R. Okay, basically I can actually relate them into what? Cosine beta and tangent beta, if I want. Okay. So this question is quite self-sufficient in the sense, right? It gives you a lot of dimensions. Okay, so you can actually make use of the dimension that's given to you. So A to this point here is your H, okay, which is 1 meter in length. Okay. So notice from the equation, this is a Biot-Savart equation. We need ds. Okay, that means the change in my length of the filament. I need my R also. Okay, so you can see from here, right? I got my R value here. So the first thing I must do, right, is to make R my subject. Yeah. So if you see from here, right, cosine beta is H over R. Therefore, R will be equal to H secant beta. Okay, so in a sense, we have already the R value that we suck into my Biot-Savart equation. Okay, what do we need to do for ds? So you can see from here, right, we have a tangent beta is equal to S over H. Right? So that means I can make S my subject again. Okay, but this is not where I should stop there. What should I do next? I must find a ds. Right? So that means I must do a differentiation here. Alright, so I can do a ds d beta. What do I have? What do you have into differentiate tangent? What do you have in differentiate tangent? You got secant square, right? Okay, so if I differentiate ds with respect to beta, okay, I have this equation here. I hope you all can understand what I'm doing here. Okay, basically I'm just trying to substitute the definitions for my ds and my r, okay, using the trigonometry functions that's given in this question. Alright, so remember what does this x mean? It's a cross product of two vectors. Okay, so ds is your length, is a length, r is your length, so there are two different vectors that we are considering. Okay, so therefore, right, before we can do anything, we can just now substitute my ds, which is my h secant square beta, and my r as h secant beta into this equation here. Okay, so I will just do that. Okay, so I'm just replacing my ds now. Okay, I think I've done this derivation for you before. So just remember, okay, you do ds cross r. That means, right, if I make this into a scalar quantity, is what? It's the magnitude of ds times the magnitude of r times what? The sine of the angle between ds and r, right? Okay, so if this is beta, right, what is this angle here? Anyone? This is 90 minus beta, right? Okay, so remember, right, we say, right, if I do a ds cos r, I should have a ds r sine theta. Correct? Okay, so that's the definition for your cross product. Okay, the magnitude of ds times the magnitude of r times sine theta, where theta is the angle between ds and r. Right? But now the angle that we have, right, is not theta. Our angle is actually what? Sine 90 minus beta. What is sine 90 minus beta equals to? Cosine beta, right? Okay, this is equals to cosine beta. Okay, you know why? Sine 30 is cos 60, sine 50 is cos 40, right? So it's just complementary. So therefore, right, if I understand this math over here, okay, the next thing I can do, right, is to change this into, okay, my r cos beta here, because my sine 90 minus beta will become my cos beta. So from a cross product, okay, it becomes all these are scalar quantities here. Okay, I think I've derived this many times for you already. Okay, so the difficult part to me, right, is from the first line to the third line here. Okay, so it will be up to us, right, the next step, however you want to cancel the equation. So in a sense, right, you can actually change, you can start to cancel your r's away if you want. Okay, or you can change your r into your h secant beta. Okay, whichever is easier for you. Alright, so for me, right, I prefer to change this into h secant beta. Okay, reason being, right, I can just simply cancel them off if I want to after that. Okay, so at the end of the day, right, no matter how the question is, especially for such a case, right, where this is like the whole span of the wing. Okay, this is your left wing, this is your right wing, wing tip, sorry. Okay, so you realize that at the end of the day, I still get the same answer. Okay, as how I have derived this for you last week. So as I said, right, the difficult part really is to change from your first line to the third line here. Okay, the rest, right, is quite simple because your circulation is a constant, your 4 pi is a constant, your h is also a constant. The only thing I have to integrate actually is my cosine beta here. Okay, so in the past, are we all at this point? Okay, so last week, right, if you remember what I said, okay, if right, I'm doing across the whole span of the wing, okay, I'm looking at what? Minus b over 2 to b over 2, right? Okay, or if it's angle, right, it's minus pi over 2 to pi over 2, right? So it's from the left wing to the right wing. Yeah, the center of the wing is y equals to 0. Okay, but in this case, right, I'm not concerned about from here to here. I'm not looking at this filament here. What filament am I looking at? I'm looking at this filament here. Okay, and in a sense, right, I'm looking at the displacement between the top point to the lower point. Okay, whereby this length is 0.01 meters. Okay, so that means my angle, right, cannot be just minus pi over 2 to pi over 2, right? Because minus pi over 2 to pi over 2 is for the whole wing, yeah, in this direction. Okay, but I'm just concerned about this particular filament here, okay, which is 0.01 meters in length, right? So what do I need to do? Okay, so I still need to make use of this equation here, right? But angles that I have, right, will be slightly different. Okay, so what do I mean by this, right, is this. If now I have known, right, my ds, am I going too fast? Am I going too fast?
Can go back to the previous slide.
Haven't finished copying, is it?
Yeah.
Okay, I thought you're copying, but I take a picture. This is what I've gone through before, anyway. It's the same thing that I've derived from it. Okay, but the point I'm trying to make, or the distinction between this and that is this. For this case, right, okay, I mean for what I've derived for you, okay, is from the left wing tip to the right wing tip. Right, that's what the range, right, is from minus pi over 2 to pi over 2. Okay, but for this case, I'm just looking at this isolated filament here. Okay, where the length that I have, right, is 0.01 meters, given in the question. Right, so can I move on now? Okay, so in a sense, right, what we have is that this ds here, or this filament here, is 0.01 meters. Okay, as given the question. So I need to know, right, is from this end to this end, what is the angle that I have? Okay. Okay, these two lines that I've drawn, okay, is from one end to the other. Okay, what is the angle difference there? So we know, right, we have derived just now from the first equation, we have a certain beta there, which is an arbitrary angle. So I can actually find the first beta that I want at the lower end of the filament. Okay, the change in angle will be from beta 1, okay, to beta 2, right? And beta 2 is at the other tip of the filament. Okay, so it's quite easy because we know the dimensions that are given to us. Okay, so actually you can find what's beta 2 quite easily, right? Or if you want to find beta 1, it's also quite easy because if this is square root 3 meters and this is 0.01 meters, you should know what's the difference here anyway, correct? Okay, so let's try beta 2 first. What is, let's say, sine beta 2 equals to? Okay, why do we look for sine beta? You don't know why? Okay, because, right, let me just go back to the previous equation. Here, right, if I integrate this, what do I have? I'll get sine beta, right? Okay, so the focus that I should focus on, okay, is what is my sine beta equals to? Okay, so sine of any angle, right, is the opposite over the hypotenuse. So sine, this is the opposite, right? Hypotenuse is here. Okay, so it's just your square root 3 square plus 1 square. Okay, your hypotenuse length. Anyone got any problem here? Understand what I'm saying here? Okay, how do we find sine beta 1? What is the opposite length equals to? It's square root 3 minus 0.01, right? Okay, so you can do the similar thing for beta 1. Okay, so with these two, right, okay, I actually know the limits, okay, of the integral that I want to integrate already. Okay. Okay, so with this, we can then do the math. Okay, this first line was what we have done the previous slide. Okay, now we just need to change the limits of negative infinity to positive to beta 1 and beta 2. Okay, then take out our constants, get our sine beta 2 and sine beta 1. Okay, you can get the answer. Anyone got any questions here? So the direction is normal to the paper. The reason is because of this. When you have a induced velocity, it's a vector as well. So remember what I said, right? The cross product of two vectors, okay, based on the definition of the Biot-Savart law, is still a vector on its own, right? So two vectors, when you do a cross product, you get a third vector. The third vector, right, is always perpendicular to the two vectors that you have. That's why it's actually normal into the paper. Okay, because it must be 90 degrees to both my ds and my r. Okay, so ds and my r, right, if you look at this, is a 2D plane. Right? So it's either the vector is going into the paper or out of the paper, depending on the direction that you specify. Okay, the other important thing is this: if I do a filament analysis at point C, okay, and I want to know what's the induced velocity at point A to point C, you realize that there's actually no induced velocity because beta 1 and beta 2 is 0 degrees. Alright, and therefore, right, the V value will be 0 also. Okay. So this for example and the previous for example that we went through last week, okay, is based on the same equation that we have. Okay, the difference is just what is your ds and what's your r. Okay, and what's the angle between your ds and your r. Alright, and then you can change the limits based on the question that's given.
Prof, what does this V equal to?
This is your induced velocity, okay?
By the winglet.
Caused by the circulation at the filament here. So that means, right, if there's some rotation here, okay, if I were to have somebody standing here, right, I'll be pushed into the paper by the circulation. It's the same as what I said last week when you have takeoff, right? You have to wait before you take off, right? It's because of these vortices that's generating. So if somebody is behind you, okay, if the V is big enough, right, you actually push you down. That's one implication. The second implication which you're learning here, right, is when you have a wing analysis. Okay, this circulation itself causes this thing called induced drag. Okay, because it pushed your angle of attack downwards as well. Okay, that's why we need a stabilizer at the back of the wing of our plane. Okay, primarily for this reason. So the wing nut is very important because the wing nut, right, can alter, okay, the induced velocity that we have. Yeah. You just imagine if I don't have a wing nut, right, that means I don't have 0.01 meters here. I have nothing to minus here. So my induced number will be much, much bigger. Yeah, but having that wing nut there, okay, I have some things I can take off, take away. That's why my induced velocity is less. Remember, V is a vector. So its velocity is a vector. When there's velocity that causes acceleration, when there's acceleration that causes force. Right? So there's an induced downwash that will happen. Okay, are we all done with this chapter? Okay, so this chapter, right, okay, is actually on a very important law or a theorem called the Biot-Savart law. Okay, but basically what this is telling us, right, is that if whenever the circulation is a two-edged sword, it causes lift, okay, which we'll learn later on. Okay, but it also causes induced drag, okay, in the form of this thing called induced velocity. Right? Okay, so next semester actually we'll be able to quantify what is this value equals to. Okay, can you all take out your next lecture note, please? You guys all have your notes here with you? Have, right? I think I sent this last week. Okay, so this chapter 4, right, actually is really the last chapter that I will go through, right, in terms of fluid mechanics. I think many of you are already doing this lab already or have done this lab already, okay, understanding the source, sink, double, and so on and so forth. And many of you have many questions also on the lab. Okay, so hopefully through this series of lecture, maybe you can understand a bit better on what the lab is actually asking you, right? Okay, so you will see, right, we will progressively move from fluid mechanics, okay, the first 4 points here, okay, eventually into aerodynamics really. Okay, when we talk about Kutach-Chaykovsky theorem, okay, this is where we talk about the lift that's generated by circulation. Okay, so we are moving to the realm of aerodynamics here. Okay, so there are some theorems that we have to know, okay, but I don't think I will be covering this today. I'll probably be soon. Okay, so today's lesson I think is still a revision to you. Okay, because if you have done Prof. Simon's lecture and the lab, right, I think you'll be able to understand what I'm saying here. Alright. Okay, so what we have covered so far is this. Okay, I have derived some equations for you. Okay, namely the equation known as the Euler's equation. Okay, so that was done by what? Conservation of momentum. Okay, where I talk about the rate of change of momentum. Okay, then from there I simplified that into the Bernoulli's equation. Okay, and when I did that, right, there were a few assumptions that we make. One was that it's an incompressible flow. The other one was that it's an irrotational flow. Alright, so when I talk about incompressible flow, okay, we use conservation of mass, that is a continuity equation, okay, to help us to understand that. Okay, and this is the first equation that we have. du dx plus dv dy equals to 0. Yeah, so u is your axial velocity, v is your vertical velocity, x and y is your two dimensions, your x and y axis. Okay, so this is the physics behind that. Okay, we talk about conservation principle. But the math behind this, right, is actually what? Okay, we have this here, right? The divergence of a vector field, okay, give us this equation here. Equals to, why is it equals to 0? Okay, because mass is conserved in this question, in this assumption. Right? So that means anything that changes with respect to time will be equals to 0. Okay? So the second equation that I mentioned to you guys, right, is on irrotational flow. So when I talk about irrotational, okay, we talk about the fact that the vorticity is equal to 0. Alright? So when vorticity is equal to 0, okay, we have this equation here. dv dx minus du dy, or delta v over delta x minus delta u over delta y equals to 0. Okay, what do we have here? This is what? The curl of the velocity vector.
please note the subtlety or the difference in this. Okay, this is du over dx. That means it's your axial velocity over your axial distance. Yeah, this is your vertical velocity over your vertical distance. But when you talk about rotational flow, it's different really. Okay, you cannot. This velocity gradient, right, is different from. That means if you have the axial velocity, okay, it must go in the vertical direction. Okay, please think of this difference. It's very very important. Okay? Do you have any copy here? Must copy it. Right, so these are two very important equations that you have to use quite frequently. Right? Okay, so then also in the last lesson, right, we talked about other two variables, okay, namely your velocity potential, okay, and also your stream function. Okay, so remember what I said, right? We say your u and your v can be related to both your velocity potential and your stream function. Okay, the first one, or rather the second one that we have was this. My axial velocity is actually equals to the change in my velocity potential with respect to x, and this is my v velocity. Okay, so this one we have to memorize because you will not be given this. So, but the thing is, right, in a sense, if I know my u or my v velocity values, okay, or expression, I can then be able to find my velocity potential expression also. Okay. So if I were to combine this equation now with the fact that it's an incompressible flow, okay, I can actually get this second order differential equation here. Okay, that means delta square phi over delta x square plus delta square over delta y square is equal to 0. Okay, so u and v, right, as I said, can be expressed in terms of velocity potential and also your stream function, right? Okay, so these two are extremely important, okay, because if I know one variable, right, I can find the other two variables, okay, in terms of my velocity potential and stream function. Okay, so I can do the same thing now, right? Because if I know u and v, okay, I can also use my e-rotational analysis. Okay, I can also find out the second order differential equation for my stream function also. Okay, and I think if you have learned this, right, you know that this is actually known as your Laplace equation. Have you guys learned Laplace equation already? No? Have you learned Fourier series? Yes, Laplace over the head. You should learn it, right? Not in this form. But it's actually the same thing. Because if this is inner x squared y squared, I can do x y equals if I want. Right? By just a second order differential equation as well. Okay? So you can see from here, right? I have this plus this equal to 0 and this plus this equal to 0, right? It means that actually I can combine both the equations together. Okay? So what is the relationship between your stream function and velocity potential? Can you all remember? How is stream function related to velocity potential? They are always 90 degrees to one another. Okay, that's why, right, if I have a streamline flow, that means I only have the stream function, okay, I will not have any velocity potential. But the moment, right, I start to recirculate, okay, then I will have these values here. Alright. Okay, so that means, right, if this is a summation of terms here, okay, where we have in terms of x and y, okay, it just tells us, right, for anything that we do, if you want to go through the Laplace equation, okay, you can actually sum this all out as a solution. Okay, later I'll show you what's the meaning of that. Okay, so in the sense, right, it's just saying that if I want to find the total stream function, okay, of a different combination, then what you have done, your uniform flow plus the source and sink or doublet, right? Okay, we can actually add up the stream function values together. Okay, this is the beauty of stream function and velocity potential. Because when we talk about velocity values, right, we cannot just add the different velocity values up. But if we can quantify that in terms of our stream function, okay, of our velocity potential, we can then start to add this up because of this definition that we have. Okay, so this is known as superposition. Okay, so what is the meaning of superposition? Okay, or what's the significance of superposition? Alright. The significance of that, right, is that we can actually allow us, right, to build, okay, that means to add up different flows together. Okay, whether is it a uniform flow, add with a source or doublet or vortex, okay, we can add up the different flows regime together, okay, and come up with a new flow behavior. Okay, I think you all learned this thing called the Rankine half body. Okay, so I'll explain to you how you get the uniform flow. So for example, right, the most classical way of doing things of this superposition theory is this. We can actually construct this thing called a lift insulator, okay, which is the last superposition that we will do. Okay, when we have a vortex and a uniform flow, okay, we'll cause this thing called lift to be generated. Right, so I'll cover that later on also. Right, there are 5 elementary flows that you have to consider. Okay, these are the 5 flows that you have learned, I think, already. Okay, so you have uniform flow, you have your source and your sink. Okay, you have a doublet and your vortex. Okay, I believe right in your lab you have probably done the first 4, if I'm not wrong. Okay, where you have uniform flow, right, you turn on the source and the sink. Okay, and then you turn the source and sink close enough. Okay, it becomes this thing called a doublet. Okay, vortex is what we learned last week. Okay, so a vortex and a source and the sink, right, they behave differently. Okay, even though the shape is the same. Okay, what is equal to 0 for vortex? Can anybody remember? How do we quantify the velocity in vortex? Is it in u or v, or is it in vr and v theta? Vr and v theta, right? What is vr? What does vr stand for? Anyone? Your radial velocity, right? What is v theta? Anyone? Your tangential velocity, right? For vortex flow, what is equal to 0 for vortex flow? Obviously, no one remembers what I said. Okay. So for vortex flow, okay, there's no radial velocity. That means the vortex, right, remains in its own shape, okay, but it has a tangential velocity, okay, v theta. Okay, your VR is always equal to 0, your V theta, right, is equal to some value that you have. Okay, and that's known as your, either you call this as a circumferential velocity or your tangential velocity, is the same thing. Alright? But for a source and a sink, okay, they're different. Okay, for the source and the sink, right, your V theta equals to 0 because it's not circulating. Alright, but your VR is a certain value because it's radiating outwards. Alright, so like I give you an analogy before, right? Remember, I said to you like for a source and a sink, it's just like throwing a pebble into a pond of water, right? The radius of the wave that will expand outwards. So there's a certain radial velocity that we have. Okay, but it's not circulating at all. Right? Please, this is very, very important, okay? So please try to at least differentiate between these 2 flows that we have. A source and a sink is the same thing, right? Source is just going outwards, sink is going inwards. So it's just a direction change in the velocity, that's all. Alright? Okay, so for uniform flow, okay, when we talk about uniform flow, which is the simplest, okay, we are looking at this as a constant velocity value. Okay, so we can consider, right, a uniform flow can have 2 components if it's a two-dimensional flow. Okay, I can have a u velocity. Okay, I can also have a v velocity. Okay, as I said, right, velocity is a vector, so we can actually resolve, okay, this into a total velocity that we want to have. Okay, in most flow, right, okay, if I say that this is an axial flow, it just tells us that my u, right, is so much bigger compared to my v. Yeah, I mean the real flow that you see, let's say an aircraft that's flying, right? Okay, whether it's straight level flight or when it's taking off, right? U is always the dominant flow, am I right? Unless you are taking vertical takeoff, right? Okay, but in the civil jet, right, U is always the dominant force or the dominant velocity that we have. Okay, so V, right, is always considered to be very small. Okay, but it's not equal to 0. Just like when compared from V against U, V is very, very small compared to U. You understand what I'm saying? Okay. So we can consider V to be very small compared to V about 0 meters per second, but it's not always 0. Okay, because even in straight level flight, right, if you go through turbulence, your aircraft is bumping up and down. So there's always a V velocity that you must have. Okay, but an aircraft is designed to move forward now, correct? So the U is always so much bigger than V. Okay. so that's something that we have to consider also. So that's why even if I want to draw a velocity triangle, right, for my velocity, I cannot discount the fact that there's a v value that I must consider. Okay, regardless of how small it is, okay, there's still a certain v value that you must consider. Alright, that's why because of that, right, okay, we can always resolve our v value, okay, in terms of u squared plus v squared. Alright, okay, so we know, right, okay, from two sides away ago, okay, we have my u and v can be in terms of my stream function. Okay, so if I want to find out what is my u and v, right, I can actually find based on this. If I integrate this, for example, okay, what do I have? I get a stream function that is equal to uy plus a function of x. Okay, we did this exercise before already. Okay, so why do we do this? Okay, this is because this is a partial differentiation. Okay, that means my stream function is in terms of both my y and my x. That's why I must put an fx here. Yeah, but I can also find the fx if I want. That means if I integrate the next term here, okay, I can also find that my stream function is a function of x also. Okay, so if I combine these two equations together, actually I'll get this uy minus vx. And this was what I've given to you also. Okay, I think it's last week or the week before, when we developed the potential flow theory. Okay. So this tells me, right, my stream function can be in terms of my u and my v also. Yeah, so I wanted to give that in this form. Okay, but as I said, because my v velocity is always considered to be equals to 0, okay, the only flow that I consider is my u. Okay, but this is a complete equation for my stream function. Okay. So likewise, if I do the stream function already, I can do the same thing now for what? For my velocity potential. Okay. So by the same token, right, as we have done for the stream function, can you all try this? I don't know if you need to copy anything, but you can. I think you should be able to do this. Now, if I integrate the first term here, how is my velocity potential equals to? It will be ux plus a function of y. Yeah. Okay. So same thing. Okay, I can do for the next term. I get what? My stream function equals to what? Vy plus a function of x. Okay, so I have this term. Okay, that means, right, if I combine both together, my stream function is equal to ux plus vy. Okay, as I said again, this is a combination of both my u and my v velocity. Okay, but the question, right, if the question says this is a pure axial flow, for example, that means my v will be equal to 0. Okay, so I don't have to consider this vy anymore. So what does all these things that we do, right? What does it mean actually? Okay, so I will give you an example in the next slide. Have you finished copying already? Okay. So for example, right, in this slide here, okay, we have a stream function that is equals to 3y minus 4x. Okay. Now for this equation, we can do something really. We can actually find out what is my u velocity equals to, and also find my v velocity equals to. Right? How do I do that? Okay, I know the relationship of u and my v. Okay, in terms of the partial derivative of my stream function here. So if I do the differentiation, I can get u equals to 3 and v equals to 4. They are going in both directions. It's a two-dimensional case. That's why you can see from let's say this equation, right? My stream function is both in terms of u and v, okay, in x and y direction. So it's a two-dimensional equation. Unless I went to 1D straight away, right? That means my velocity potential will just be equal to ux, that's all. Okay? If you're asking me because of this of the left, for example, right? Actually, you're just looking at ux, okay, because it's dominant in the x direction, so. Okay, let me just go back to this. So we have this, right? You have u equals to 3 and v equals to 4, right? What does it mean actually? It just means that I can find out what is my total velocity, right? What is my total velocity equals to? What is that resolved velocity that we have? Square root 3 square plus 4 square, right? So I get what? My v total equals to 5. so we can actually do some graphical representation of what this equation is telling us actually. Okay, so for example, right, now we can actually plot the stream function in terms of some values at hand. So n is any values. Okay, so from 0 to infinity if I want. Okay, so let's look at this. Okay, for example, right, do you remember the definition for stream function? Stream function represents for one streamline, right, across the blunt body, right? And along every streamline, there's only one stream function value, correct? And the stream function is a constant value. So a stream function is always a number, just a constant value, right? It can be positive or negative, doesn't matter. Just going in different direction, but it's just one value along the same streamline. So right, let's say if I put the stream function as equals to 0, okay, if I put stream function as equals to 0 here, I'll have 3y minus 4x equals to 0. Okay, that means right, I can do one more step to say that I can know my y as a function of x here. Okay, this is just pure math here. Okay, I'm trying to draw the graph for you now using this equation here. Okay, so if you can just follow me, stream function can be any value. Okay, so I start from 0. Alright, now I can try equals to 1 also. Okay, if I try equals to 1, I have 3y minus 4x equals to 1. Okay, so I have a new equation. I have y equals to 1 plus 4x over 3. Are you following me so far? Okay, so basically, I'm not doing anything except doing some transformation of my equation. Okay, just adding up some values there. So if you were to expand 0 and 1, that means you carry on with this, right? The 2, okay, what do I have? I have y equals to 2 plus 4x over 3. Okay, so I can go on. I can go from 2, then 3 to 4 to 5, all the way right until n. Okay, so if I go until n, I have y equals n plus 4x over 3. Okay, so what do I mean by that, right? Is I can actually plot these stream functions now. Okay, because you can see from here, right? I can change my x value. That means if x equals to 0, okay, I have some y value. If x equals to 1, I have some value. X equals to 2, I have some value also. Alright? Okay, so if I just plot this as a table here, okay, for every stream function value, okay, 5 equals to 0, 5 equals to 1, 5 equals to 2, 5 equals to 3, all the way until 5 equals to n. Okay, I have this data here. Okay, now this is all. Okay, what kind of equation is this? A straight line equation or is it a curve equation? Yeah, it's just y equals mx plus c, right? Basically, if I just put in x values here, okay, as long as I got 2 points actually, I can just draw a straight line really, right? For every stream function values that I have. Okay, so if I plot this out, okay, what I will see is this. Okay, equals to 0, equals to 1, okay, or 2, 3, 4, right? I got all these different values that I see here. Okay, so this is just a stream function because these are all these values here. Every line represents a streamline. Okay, and every streamline, okay, has one value of stream function. Okay, that means it can be 0, it can be 1, equals to 2, or 3, or 4, and 5. Okay, so that's a stream function. Okay, so the question is, how will the velocity potential look like? Anyone? It has to be perpendicular. Okay, so like what I say, right? If it's a streamline flow, that means there's no rotation. Okay, what will this value be equals to? It will be equal to 0. Please remember that. Okay, if it's an irrotational flow, right, that means this will always be equal to 0. Okay, that means there's no rotation, so all the flow will just be pure streamline, right? Okay, so uniform flow. Okay, we have done what u and v, right? We have stream function and velocity potential. Okay, but based on what I mentioned last week, right? Okay, there's one more coordinate system that you cannot forget. What is the coordinate system? Please, what's the coordinate? It's a polar coordinate system. Why do we need polar coordinates? Because when we talk about source, sink, or vortex, right? Okay, it's all circulation flow, right? So we need our polar coordinates. Okay, so therefore, right? If I want to do this superposition, right? Whether is it uniform flow or vortex flow together, right? I cannot have one Cartesian flow. I cannot have one polar coordinate system. Either I do all in polar coordinates or I do all in Cartesian. All right. So for us, there's a need for us also to remember this. Okay, that means we must change our u and our v. Okay, in terms of our polar coordinate systems here. So just now, right, I gave you two equations. I gave you stream function. Just write this here. I say this is equals to my uy minus my dx. And I say this is equals to my ux plus vy. Do you remember this equation? Okay, so this is the general equation for my stream function and velocity potential. Y and x, right, represents they are all in one Cartesian form, right? So now we know that x is r cos theta, y is r sin theta. So that means right, I can change this into my polar coordinates form if I want also. Yeah. Okay. So the first thing I can do right is that I can change my y and x. Because if y is r sin theta, x is r cos theta. Okay, I can have these two equations. Right. So r sin theta is my y, r cos theta is my x. Okay. So I have this equation here. So if right, I want to put it more general. That means right, I want to have this certain angle of attack. Okay, especially if I have a aircraft that's taking off. Okay, I will have an alpha that I can have also. Okay, so instead of having just my u and v, okay, I can express my u and v now in terms of my v total velocity. Okay, now how is u and v total related? Anyone? How is v total related to u and v? Okay, it's u squared plus v squared, right? Now, if I want to resolve this into my components, what do I have? What is u equals to? So I can say, right, cosine alpha is equals to what? U over v total, right? So that means my u is equals to v total cosine alpha. Agree? What about v? Oops. Okay, so v will be v total sine alpha. Okay, so what I'm trying to do here for you guys, right, is to change a uniform flow, okay, from Cartesian to polar coordinates, right? The definition for u and v, right, in terms of shape function and velocity potential will never change. Okay, it's the same definition that we have. Right? Okay, can I move on? So copying the note.
So, what the negative sign is about?
For which one?
The other one.
That's not a negative sign for this.
Why?
By definition, it's a summation of this plus this. That's why. Only for stream function, then there's a minus here. That's why you have a minus vx. Okay, so, it's a bit. Because this is stream function, this is cross potential. Can I move on? Yeah. So what I can do, right, is that if you just take a look at this, now I have ur sin theta, vr cos theta here, okay? For example, look at the stream function on its own. Okay, so I can replace now my u in terms of my v total if I want. Okay? Yeah, so I can have this equation here. That means my stream function can be v total, okay, of y cos alpha minus xl. So it's a factor that I can take out. Okay, but in the sense, right, this y and x, right, is still my Cartesian form. Okay, so what I can do, right, is to change my y and my x, okay, as what? My r sin theta and my r cos theta. Okay, so I have this second one here. Okay. So there's no difference in this equation. Okay, the blue lines, the blue one that I have is your Cartesian form. Okay, the red ones are your polar form. So the thing is, right, if I ever plot out the values, right, okay, I will get the orthogonality behavior. Okay, but my stream function is always 90 degrees from my velocity potential. So let me just ask you a question here, okay? What's the meaning of this equation? Is this, if I give you a question, right, I say that the aircraft is flying at straight and level flight. okay, or there's no incidence angle of attack, what is my alpha equals to? The first thing. What is alpha equals to? There's no angle of attack. It will be 0, right? Okay, so what is cos alpha? Cos 0 equals to? What is cos 0 equals to? 1, right? So that means, right, if I look at this as a string function, I will simplify to what? What's the value that I have if I have a flight that is straight and level and there's no alpha value? I will just because what? UR sine theta. Okay? You can't have UR cos theta. Okay, because sine alpha is 0 already. Right? So this term will become 0. Okay? So this is a general equation. Alright? In terms of both my x and y direction. But when the question comes out, right? Okay, and tell you some specific assumptions, okay, this general equation will be simplified. Okay, later you'll see one example. Right? Okay, it's the same for my velocity potential. Okay, if my alpha is 0, okay, that means my sine alpha, all this will be 0. That means the second term, all this will be cancelled. Okay, and cos 0, cos alpha or cos 0 is just 1. Okay, so the equation will be simplified. Okay, so this is the final equation or the final form, okay, of your uniform flow. Okay, in Cartesian form and also in polar coordinates form. Alright? Okay, so please remember this equation. You're not the okay, sometimes right in the question exam paper they will give the equations to you, but sometimes they don't. You're supposed to derive this on your own. Okay, but at least you need to memorize these equations.